So what I made here is a molecular dynamics simulation of graphene. So this is a tiny piece. What happens here is that whenever the chemical bonds between the atoms goes red, it means they're strained. So it's sort of when I start to pull it, it becomes red. And after a while, it relaxes and finds its equilibrium structure. So you see it runs really quickly here on the screen, but also if I increase the size of this to a much bigger piece here, maybe make the atoms a bit smaller, you can see it actually still runs really efficiently. So you can see now it started by being a little bit distorted, and after a while all these red bonds, they are quietening down, and it's finding now its equilibrium structure. But I have still the possibility of pulling one atom here, so I can demonstrate, or the students can see what happens if you pull the crystal. And you can also see that these sort of red waves are spreading out from this distortion point. These corresponds to phonons, and the speed at which these waves are traveling through the crystal corresponds to the speed of sound in graphene. So this is a phenomenal way of illustrating some really important physics and some phenomena in a way that is intuitive and direct. You can see that as I stretching these bonds here, I'm pulling the crystal a little bit downwards, and as I let go, just like a system of springs, these sort of distortions, they progress throughout the crystal. So that's also how heat transport, like thermal conductivity, works. It also is a progression of these sort of lattice distortion throughout the crystal. So what it blows my mind is that this is running on a laptop that is also recording video at a reasonable frame rate at the same time. So it's somehow running this in HTML with JavaScript, which is something I would never attempt of doing myself. Somehow works fast enough that you can use it for a really compelling demonstration, or also as a basis for experiment where the students, they learn to apply more sophisticated potentials of these bonds, include bond breaking, and also play with the parameters. So this is one of my favorite digital experiments. So what I can also do here is I can simply pull the whole crystal here along. It runs a bit slower now because I'm recording the screen at the same time. But you can see I can also actually create defects and disorder. So actually, no, it didn't really work. But I should be able to pull some atoms apart and really create an area where the bonds are broken. And but I can also start to kind of repair the crystal. I don't know how physical this is, but it's pretty interesting to see how the crystal kind of recovers the equilibrium shape whenever the atoms are put in the positions where this is possible. So you see I'm kind of slowly fixing I don't know. Yeah, it's getting there. You see the damage is nearly repaired, and this shows that the graphene lattice is quite resilient and also very good at repairing itself. And this is something we also see when we do chemical vapor deposition, and also when we perturb the lattice, for instance, with an electron beam, that will allow the atoms to shift around, and if it can, it will try to recover the damage and create a perfect graphene lattice even after very severe introduction of defects.